Okay, we're back. So this last problem, number 29. Oh boy, here's what we have. We have a finite projective plane model, and from this, so what is this model? Well, I'm taking it for granted that this is a finite projective plane. What is the points are here are being represented as numbers, and the numbers that have been grouped together here in the set is meant to be, the line through those numbers. So this is kind of the most abstract way in which you can be presented with a finite projective plane. That's really what a finite projective plane is. The pictures are just there for our puny little brains. Really, it's just a set of points and a set of lines and an explanation of which points are on which lines, the incidence relations, and that's what this is. As I was saying in the video that I recorded last year, the only way that it could be even worse than this is if it wasn't given to you as numbers, if they were just given to you as some kind of objects or something like that. But actually, I don't really even think that changed anything. Okay, so what do I do with this gigantic mess? All right, well, Gossett has presented it to us in a way that's at least a little bit clear, because within each line, he's written the numbers in increasing order. And also he used the numbers 1 through 21. And so, okay, this is a finite projective plane model with 5 points per line. So this is a finite projective plane of order 4. And from this, we are going to extract the sort of affine model of order 4. And then from that, we will extract the 3 mutually orthogonal Latin squares. And what we're really going to do is just extract the 5 squares, which 2 of which are going to be those squares that are technically not Latin squares, but it's their orthogonality which makes them Latin squares. Okay, the other ones. All right, you'll see. All right, so what can we do? Well, we need to first figure out which lines are in an equivalence class together. And it really doesn't matter if you take all the lines that go through a certain point. The way these have been listed suggest, based on numeric order, although that's totally irrelevant, that the 5 highest numbered points are 17, 18, 19, 20, and 21. So I'm just going to assert that this line is the line at infinity. Now I claim that there's nothing really special about this line actually, and that I could just permute all these numbers. I could swap every 7 and every 5, and I could swap every 19 and every 1, and it would still be a perfectly good finite projective plane. So it's completely arbitrary which line you designate to be the line at infinity, but I shall designate this line to be the line at infinity because the numbers are biggest. Having done so, having designated that line as the line at infinity, I have now basically forced any line, then these points are the points at infinity. And thus, I have grouped my lines by I have now grouped a bunch of lines together, namely all the lines that go through point 17. If I'm thinking of point 17 as my point at infinity, then all the lines that pass through 17 are all parallel to each other in the affine model. So I will now put a green box around the 4 lines that have a 17 in it, and I'm now going to interpret these 4 lines as being parallel. Okay, and now this is the part I haven't really practiced. I'm not really sure what the hell I'm doing, but I think it will just work out somehow. So I'm just gonna start. I'm just gonna go 1, 2. Yeah. So the thing that's kind of weird is I'm just gonna call this 1, 2, 4, and 9. I really just think it doesn't matter. I hope it doesn't matter. And I'm gonna call this 3, 10, 11. Perhaps I should have practiced this first. And 13. Okay. And then I'll go to the next one, 5, 6, 7, 8. So what I think what Gossett would want you to do instead of doing what I'm doing is engage in an extremely long, tedious permutation exercise in which you basically swap 9 and 3 universally throughout this entire model, swap the numbers 9 and 3, thus forcing this first line to go through 1, 2, 3, 4. Then I have this line 5, 6, 7, 8, and then I have this 9, 10. I might as well actually, it's possible that I should do this. I just don't want to, and I'm hoping I don't have to. And then I would have 9, 10, 11, then I would swap 12 and 13 universally throughout the entire model. I've done this before. It takes like a long time. So I'm trying to get away without it. Let's see if that works. So I'm just going to force my grid to be like weird like this. And this last one is 12, 14, 15, and 16. Okay. I basically let the numbers in this class of lines, I let it determine that my horizontal lines are going to be these ones. And I'll now draw these horizontal lines, and there we go. That's one equivalence class of parallel lines. Okay, what have I accomplished so far? Nothing. Okay, what next? I think I can just kill these now, so I'm just going to put lines through these, because they're just done. Okay, next, let me go to 18. Oh, and so all of these lines meet out at this point 17 at infinity, and I just delete that point 17, it's gone. So that's, okay. Now I want the vertical lines. So let's take 18. It's possible that Gossett threw us a bone here. Okay, so let's see, 1, 3, 5, 12. Ooh, that's very promising. So there was nothing particular about 18. I think I just got lucky or something. But 1, 3, 5, and 12 all go through that line. And then let's look at the other, what's another 18? 7, 9, 11, and 14. Well, this time I didn't get lucky, did I? Where's the 2? I need the line that goes through 18 and 2. And by the way, this might be a good time to note that because it's a finite projective plane, there must exist a line through 18 and 2. Well, actually, let me just box all the 18s. So there's one, and yeah, this is going to work out great. We don't need any of this permutation crap, Gossett. 2, 6, 10, 15 is another line, right? Well, look, 2, 6, 10, 15. Gosh, I wish that was a 15 there and not a 14. Well, I don't see any particular reason why it can't be. So I'm going to swap 15 and 14. After all, the only reason I wrote 12, 14, 15, 16 is because that happened to be the order that it was written here, but this is just a set of numbers. There was nothing special about 12, 14, 15, 16, 17, just that they were all collinear. So I'm now just going to choose to do it this way. And I choose to do it this way so that I can write my 2, 6, 10, 15 line. And there it is, 2, 6, 10, 15. This is great. So I'm done with this line I've used. I'm done with this line. 4, 8, 13, 16. Well, 4, 8, 13, and 16, well now I'm just going to do that same move again, and I'm going to call this 9, and I'm going to call this 4. And so now I have 4, 8, 13, 16 like this. And finally I have the line 7, 9, 11, 14. Okay, so this, what I have just done is converted into picture. I've sort of like forced my numbers now to go into a grid. And now I've done sort of the easy part, right? The easy part is I have lines. I have the horizontal lines and I have the vertical lines. And I'll put a line through this too, because these just all got deleted in round, because I deleted the point at infinity. Oh, and I'm deleting point 18 now. Okay, so now it actually gets hard. So let me switch to purple. So now I have 19. So what's 19? Well, all the lines which share a 19 are all parallel to each other in the affine model. They meet out at point at infinity 19. So now I don't think it matters where we start, 3, 8, 9, 15, 19. So 3, 8, oh gosh. I don't think I want to actually draw this though, is the thing. 3, 8, 9, 15, 19. So 3, 8, 9, just 3, 8, 9, 15 basically. Okay, so I'm just going to put a little, 3, 9, 8, 15. I'm just going to put little checks there. But now, I'm not even going to draw these lines because it's just too distracting. What matters though is that I'm about to make a Latin square. And specifically, I'm going to make a Latin square such that one of the lines, well, here, let's do this. I'm going to make 3 Latin squares. After all, that's the goal of this whole entire thing, is to produce 3 mutually orthogonal Latin squares. I'm actually just almost done. Maybe it's more clear if I even make the sort of silly squares. So what are the silly squares? 1, 2. I just gotta get some neatness going on here, otherwise it will be bad. Okay, so I'm just gonna get these like ready or whatever. And there's one more. Yeah, neatness, so-called neatness, is not really working out. But okay, so from these green parallel lines, horizontal ones, any line that goes through a whole bunch of points, I'm just going to give them the same number. And so I'm just going to go, 1, 1, 1, 1. And these squares look stupid with the lines in the way. I've decided after making everyone watch that. I'm sorry. I'll just have to be very careful. So this is 1, 1, 1, 1, but then this is like 2, 2, 2, 2, and then this is 3, 3, 3, 3, and then this is 4, 4, 4, 4. In other words, just anytime you see a line, just produce a square in which all the points on that line all have the same number. Okay, great. What do the blue lines do? Well, the blue lines go 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, and 4, 4, 4, 4. So the first 2 squares that I extract from my figure are the sort of squares that are always lurking in the background. And now, maybe it's more clear what to do. Now, I have this 3, 9, this is just so easy. I have this 3, 9, where are all my purple, where are all my, what am I on? I'm on 19, right? So, 19, 19, and here are my other 2 19s. And what do I actually do now? I just look and I see the first one, 3, 8, 9, 15, like I was saying. So just make those all 1s. So I got a 1 here, and I got a 1 here, and I got a 1 here, and I got a 1 here. That is a little hard. Well, too bad. Then I have, just erase that. Then I have a 2, so that's this line done. Then I have 1, 6, 11, 16 is a line. Well, so now we're just going to put 2's in the 1 position, 6 position, 11 position, and 16 position. Oh my god. Cha-cha-cha. Okay, now I go to the next line. This one, I put a 3 in position 2. 5, 13, and 14. So a 3 goes here, and a 3 goes here. And finally, I put a 4's in all the positions 4, 7, 10, 12. So 4, 7, 10, 12. Boom! That is a Latin square. I know it's a Latin square because I know that it's really when I say it's a Latin square, really what I should be saying is just that it's a square that happens to be orthogonal to these 2 squares. That's what being a Latin square means. And why is the square orthogonal to these 2 squares? Because no ordered pairs, when you compare this square with this square, no ordered pairs repeat. And when you compare this square with this square, no ordered pairs repeat. And how do you know that no ordered pairs repeat? Because if the ordered pairs did repeat, then you would have a line from this equivalence class of parallel lines and a line from this equivalence class of parallel lines which intersect in two places. But that can't happen because it's a finite projective plane model, and so every two lines intersect at exactly one point. And since every two lines intersect at exactly one point and not 2 points, then you can't have one of these lines and one of these lines intersecting in two different places, and so no ordered pairs repeat. And so the orthogonality is enforced, comes from the geometry. This is the reverse of the previous process. Okay, one square down, or one interesting square down, 2 to go. So now I'll switch back to red for 20. I think I can do this kind of fast now. Of course you can turn this off at any time, because I think anyone who's watching should get this, but maybe not. So I put red boxes around all the ones with 20s in them, and now I'm going to use these lines to make another Latin square. Well, 2, 8, 11, 12, eh? So that's 2, 8 is way out here, 11 is here, and 12 is down here. Okay. Then we have 5, 9, 10, 16. So that's 5, 9, 10, and 16. Boom. 1, 7, 13, 15. So that's 1, 7, 13, and 15. This is so satisfying. And 3, 4, 6, 14. So 3, 4, 6, 14. Once again, these lines that I just finished taking care of was a bunch of lines that all met at this point at infinity 20. So they were all parallel to each other in the affine model. No one of those parallel lines that all met at point 20 could possibly intersect these blue lines. No one of these lines could intersect one of these blue lines twice because it's a finite projective plane, and so that means that none of these ordered pairs repeat, and it's therefore orthogonal to this square and orthogonal to this square, and so it's a Latin square. And then the thing is that it's also orthogonal to this square. Guaranteed that these two are orthogonal, because once again, if there wasn't orthogonal, it would mean that there was an ordered pair that would repeat, but if there was an ordered pair that repeated, then it would have to be there would have to be one line from this model and a line from this equivalence class and a line from this equivalence class which intersected at two places, and that can't happen. Okay, one more to go. Let's see, 6, 9, 12, 13. So, oh boy. No, let's do the other one first. 1, 8, 10, 14. I need like graph paper or something. 10, 1, 8, 10, 14. Okay. Boom, boom. 6, 9, 12, 13. So, what happened? Oh no, nothing happened. 6, 9, 12, and 14. No, 6, 9, 12, 13. Shoo. 13. Boom. 4, 5, 11, 15. So that's 4, 5, 11, and 15. And the final line, 2, 3, 7, 16. 2, 3, 7, 16. Okay, I won't repeat the logic anymore because I think we're clear, I think we're done. But I now present to you 5 squares which are all mutually orthogonal. And the bottom 3 are a set of 3 mutually orthogonal Latin squares of order 4. And that was the goal of the algorithm. So we are done. Woo! Goodbye.